I apologize in advance. This is going to be a bit of a dizzy video. So if you get seasick or motion sickness, probably want to avoid this video. It's going to be really shaky because we're kind of tight here in the garage at the moment. So just bear that in mind. It's going to be all over the place, no steady cam. It's going to be seasick to the second power here. So what we have here is our power supply, multiple power supplies, and I got this here because these are all going to be live. They all have naked ends here. This is going to be live when I turn this thing on. It tends to throw the breaker if they're touching the metal here and shorting to each other. So let's recap. We got the main transformer all done and it's installed, and it's going to be supplying all the control voltages and everything to the power supply. We got all the main wiring done. It's all naked, so you have to be careful not to touch something. You know, you got to be careful. We're plugged in right now, so we are live. So if you touch that, you're gonna get fried. So you don't do that. We got a switch, and we got our support power supply here because each one of these guys, each one of these FET switches is isolated from each other with a diode, so you can't just put ground here and turn each one on. We found out that the body diode causes a problem, so what we're doing is we're using another diode to cause isolation so that we don't have to deal with the body diode, and it works beautifully. Not gonna, well, you can see what my secret is right here, but you know, I'm not really gonna get into that because that's my thing that I'm playing with. You know, you do your own research. Had to put a 30 ohm bleeder resistor on here because it wasn't discharging fast enough. We got a big capacitor here, lots of reservoir. We got our voltmeter here. Each one of these is a tap, 5, 10, 15, 20, 25, 30, 35, 40, so on. So each one of these is tapped. The SMPSs are all chained together. And so if we want 5 volts, we select 5 volt tap. If we want 8 volts, we have to select the 10 volt tap. And then we have to go through the power transistor, which is over here, which has been done for a long time now, but is not ready. It's ready, but it's not ready to be integrated here because it too needs a control voltage, and we need the brain box built to do the control voltage. And there would be no interface. The brain box is all the interfacing anyway. So right now we have the negative connected to our 10 volt tap. So we'll turn on, and hopefully we won't throw the breaker. Okay, good. I don't think we threw the breaker. We got a bunch of little green lights, which is good. So it means we didn't throw the breaker. So we're going to do our 10 volt tap, right? So we got 0 volts on the meter. Cool, right? Yeah. Okay, 0 volts on the meter. We're going to do our 10 volt tap. There we go, 10 volts. And ta-da, got 10 volts. Now we're going to take the 10 volt tap off, and it's going to start discharging. Discharging. Okay. Now let's say we want 20 volts, right? So I got to change the tap here. 20 volts. So I moved it up to for the 20 volt tap. There we go. 20 volt tap selected. We got 20.3. Perfect. Okay. And take it off. Discharging. Okay, let's see. I want 30 volts. Okay, energizing for 30 volts. Cool. Okay, now let's say I want to go back down to 10. Right, it's discharging. La-di-da-di-da. 10 volts. So the switch works. Pretty sweet, huh? Okay. Discharging, say I want 40 volts. Alright, 40 volts. There we go, 40 volts, just like that. So right now it's a selectable power source. It's not smart yet, we don't have the brains in. Now each one of these taps is fully isolated from each other. They have to be fully isolated from each other or you'll cause a current loop. We suspected that, and we proved it because of the body diode and the MOSFET, which is a bitch because now I have to make more technology do whatever. But we've got 19 taps on the transformer, so we really don't care. So we're gonna select, let me turn it off first so we don't spark something, catch fire here. Turning off. All right, so we've got all these taps here. We're not going to go electro boom and smash that while it's on. That would be ridiculous because we have a fuel here, spark and fuel, and plenty of oxygen. That'd be bad. Anyway, we got all these taps. So we're going to take a bunch of these taps, and they will be AC power. And then what we'll do is we'll do optocouple to diac triac, which will feed a bridge rectifier, and then a small filter cap because we don't want these pulsing. Small filter cap, maybe 100 or maybe 1,000 microfarad, whatever, I don't know. And then that will feed the DC, so it'd be fully isolated AC being triggered by an LED, which is cute. So an LED turning on, which requires 20 milliamps to turn on each one of these taps individually, any one we want, and the brain will fire an LED no problem because you go op amp to LED. That's very easy. But if we wanted to go op amp to each one of these and try and do an isolated circuit, that would be very difficult if it's op amp with level shifters and all that nasty stuff. It'd be really ridiculous. So we could go read relay, we could go triac, we could go SCR if we wanted to, but I want about 11 volts going on each one of these so that we're really saturated when the MOSFET turns on. So we're gonna go full wave rectifier. Now we could have gone SCR. If I had 14 volts here, I could have gone SCR, but then there would still be half wave ripple, and I'm trying to opt away from that because we don't want to modulate the MOSFET because that could lead to thermal stress. It, pulsing at 60 cycles could cause stress there. So I'd rather have AC, diac, triac, opto, two triac, full wave rectified, filtered, and then we've got DC into the gate, and then it's just all LED control. We can use an LM3914 or an LM3915 as a sequential controller because it's a proportional voltage per rank, per division. So we can use a VU meter chip to drive our bank select in one IC. We don't have to use discrete op amps with Zener diodes and divider networks in order to make a voltage banking circuit. The chip already exists. So we're going to try and look at the LM3914 or the 3915, whichever one it is, I forget. One of them's logarithmic, the other one's linear. So we want something that's going to be linear because we want a proportional voltage difference between each bank. Probably about 3 volts would be my guess. I'm not sure right now. But we want some voltage overlap between the banks. So it may be 3 volts. It might be 4 volts. I don't know. We'll have to see how that goes. It might not. We might need more overlap. We might need 3 volts at the upper end and 2 volts at the lower end of overlap. It depends on how much loss is going through the system when it's under full load. That I don't know yet. So we're going to investigate that, and of course it'll work fine under low load conditions, but when we start doing 30, 35 amp load conditions, it's probably not going to work out. But we're going to try the simple approach first. If we have to go discrete op amps with individual VSATs, we could do that. I'd prefer not to do that because it gets complicated and alignment procedures get complicated, but we'll see how things go. We're only targeted for 30 amps here, but if we could deliver 35, that would be great. If we could deliver 40, that'd be even better. I'm not really sure where we're going to max out yet because this is all new territory for me, and we're going to see. The diodes right now can only really sustain like 20 amp operation before they get nuclear hot. So it's going to be interesting to see how they hold up. We're not slated for 2 sets of diodes, but really in order to make this work I need 2 sets, maybe even 3 sets of diodes for reliability reasons. And we're not there yet. This is all prototypical development work. But it works. We can test under 2 ohm instead of half ohm for our torture testing. I don't want to do that, but if I have to do light load 2 ohm, I'll do that instead of full load until we get fully capable, and then we'll talk about half ohm or even 10th ohm loads. But for the moment we're doing pretty good. This is our positive output. This will eventually feed the pass transistor, which I showed you over on the bench, and that thing's a monster by itself. So we're making progress. It's a little slow, but I think it's turning into something interesting.